This video, in the lecture on cell balancing, discusses when to balance. Both the low-level firmware consideration of interleaving balancing with accurate measurements and the algorithmic consideration of at which state of charge it is best to balance. Let's begin at the low level. The relative timing of balancing and measurement is an important firmware detail. We'll discuss it in the context of this circuit. In brown, we see the measurement pathway, the filter resistors and filter capacitors that constitute an RC filtering network, and the analog to digital converters that measure each cell's voltage. In black, we see the cells on the left and the components involved in balancing on the right. We have the balancing resistors on the PCB and the balancing MOSFET switches on the BMS chip. In purple, we have the wire harness, consisting of connectors and the wires themselves. The parasitic resistance of these components is shown explicitly. BMS ASICs are carefully designed for tiny input currents during measurement to result in tiny voltage measurement error. Even a small balancing current is likely orders of magnitude larger than the measurement input current. Say we design for a 20 milliamp balance current. 20 milliamps across the parasitic 1 ohm of the cell sense wire gives a 20 millivolt drop on each wire, for a total measurement error of 40 millivolts on that cell. That is a significant error, too much to accept in many applications. One solution is a duplicate harness with 2 wires to each cell, one for balancing and the second for sensing. Cost and mechanical complexity are often prohibitive for the dual harness solution. Another solution is to interleave balancing and precision cell voltage measurements. During balancing, the system takes coarse cell voltage measurements, sufficient for safety monitoring. On what timescale do we do this interleaving? One possibility is to do it on a timescale of hours. If the application has a daily cycle, as you might expect with solar energy storage or a family car, we might find time periods when the system is charging or discharging and we want precision measurements, and another regular time period when the state of charge is constant and balancing is convenient. Let's work through an example of what this means for a design. Let's target correcting for a 17 milliamp imbalance. That was our worst case estimate. Assume that the application spends 8 hours charging, 8 hours discharging, and 8 hours resting. That gives us 8 hours to correct for the imbalance accrued in every 24-hour time period. We can rearrange terms and solve. We need an average 51 milliamp balancing current. Since many designs cannot balance adjacent channels, we will alternately balance odds or evens. In other words, the instantaneous current is doubled since any given channel is balancing only half the time. We can calculate the heat dissipated in each balancing resistor. 0.43 watts is a bit much for a single component, so we'll need to implement each balance resistor as several series resistors. The PCB will dissipate 2.6 watts, which is high enough that some thermomechanical design is probably needed. The heat dissipation inside the chip is low enough that a chip with an exposed pad will see a relatively small temperature rise relative to the PCB. You could at this point do the analysis to see whether a chip without an exposed pad might suffice. Some applications don't have a regular rest period, or we wish to design for a lower balancing current. In those cases, we can interleave precision voltage measurements and balancing on a smaller time scale. We can monitor with high precision for 100 milliseconds or 1 second or some similar length of time, and then balance for a few hundred milliseconds or a few seconds with the consequently higher measurement error. For the precision measurement window, we should choose a duration longer than the time constant of the BMS chip's internal low-pass filter. It's also convenient to make this duration some multiple of the frequency at which the microcontroller communicates with the BMS chip. Typically, this approach enables balancing for a larger fraction of the time than the previous approach. And in turn, that enables a lower instantaneous balance current. By balancing more of the time, we can get away with a correspondingly smaller balance current. Another idea is firmware compensation. The firmware can take the voltage measured during balancing and subtract from it a value that approximates the expected voltage drop due to the balancing current. The compensation voltage Vcomp in this equation would equal the nominal balancing current times the nominal parasitic resistance between the chip and cell. The residual error will be a function of the variation in wire harness impedances and the magnitude of balancing currents. You can and should characterize this variation for a specific design, but I might guess that balance currents may vary by 30% due to temperature and component variation and aging, and parasitic resistances may vary by 50% or even more. The resulting residual error may be fine for some SOC estimation purposes, and yet, in many cases, may be too much for assessing pack imbalance. Firmware compensation is a good idea to consider and relatively low cost to implement. Let's summarize the key points in this section. Balancing current causes a voltage drop along the connection to the cells, causing measurement error equal to the product of the balancing current and the parasitic resistance between cell and sensor. Mitigations include a dual harness with separate sense and balance wires, though in practice, cost and mechanical complexity are significant hurdles. Interleaving precision measurement and balancing allows for precise measurements when balancing current is not flowing. This can be implemented with the interleaving on a timescale of hours, or fractions of a second, or both. Firmware compensation can reduce the residual error, and this is inexpensive to implement, but may not be sufficient on its own. Having discussed how to interleave balancing with accurate cell measurements, let's discuss at what state of charge to balance. Let's ask one more question around balancing. At what state of charge is it best to assess imbalance? Or at what point in the operating profile? My car might drive to run errands around town, then charge at night and rest for a few hours in the early morning. The next day, maybe we go on a day hike and drive up into the mountains, then come back and charge at night, again with a rest in the early morning. The system has a very convenient opportunity to take a high precision measurement most mornings when the battery pack is well rested and when very little current is flowing. Based on that, the system can make a fairly accurate assessment of pack imbalance and create a feed-forward plan for how much balancing needs to be done over the next 24 hours to correct the existing imbalance. Since the slope of the voltage versus SOC curve is moderately steep for the NCA cells or NMC cells in my car, where on the curve we take the measurement is not very consequential. Recall that a given measurement error, say 5 millivolts, will have a larger impact on the SOC estimate when the slope is flat than when the slope is steep. An energy storage battery used for grid stability, on the other hand, is intentionally operated around 50%. Oftentimes, LFP cells make most sense for stationary storage, where their advantages of better safety and better cycle life outweigh the disadvantage of slightly lower energy density. A battery can operate for many cycles in that very shallow middle part of the curve, where estimating SOC from voltage is very difficult. In this scenario, the pack can become unbalanced, and the voltage difference may be too small to detect in the application. To balance an LFP energy storage system battery pack, we can occasionally cycle it deeply and assess imbalance where the voltage SOC curve is steepest. Because charging to 100% is slow, in BESS applications, discharging to low state of charge is preferred. Commonly, in the BESS application, the whole system is shut down for balancing. When operators notice poor system performance, they take the whole BESS offline, the batteries are discharged, and balancing is initiated. The batteries remain at low state of charge until balancing completes, and only then the system returns to operation. I am baffled by the inefficiency of this. Here's what I'd recommend. Oftentimes, grid energy storage involves multiple battery packs. Select one of the multiple packs for deeper cycling. Discharge that one pack to nearly empty and balance it, while the rest of the BESS continues to operate as usual. Then, return the one pack to normal operation. The trick is coordination. Balancing is usually thought of as something that a pack does internally and implemented thus. The idea on this slide requires a central controller to coordinate the packs and requires each pack to communicate some estimate of its imbalance externally to indicate that it might need balancing and also that it is done balancing. A typical architecture for a stationary battery energy storage system groups perhaps 12 to 14 cells in series into a rack with an associated BMS. A central controller, called an EMS, Energy Management System, communicates with and manages all the racks in the system. The EMS could then, occasionally, select a specific rack for deeper cycling. From what I've heard, this level of sophistication, unfortunately, is not widespread in the BESS industry. Let's summarize the key points in this section. Balancing and assessing imbalance don't have to happen concurrently. Assessment of the imbalance is best done when the battery pack is rested and at a steep part of the OCV-SOC slope, which is challenging for LFP packs operated mid-range where the slope is very flat. You may recall from earlier lectures that LFP cells are safer than NMC cells in the sense of having less proclivity for exothermic behavior. And the lower energy density of LFP cells is a relatively minor drawback in the stationary application. This makes LFP cells well suited for stationary energy storage applications. However, LFP cells' flat OCV-SOC slope makes the state estimation more difficult. More sophisticated controls between the BMS and EMS can address this challenge. In this bonus slide, I'll tell you about a controls idea that I think is worth considering, in particular for batteries where a non-operating state is infrequent. For example, a BESS with the standard approach might operate for several months. Because it's mostly operating in the middle of the SOC range, and because it's built with LFP cells, normal operation doesn't provide opportunities to assess the state of imbalance. From time to time, the battery pack is taken offline, discharged and rested, such that the state of imbalance can be accurately assessed. The pack then spends some hours or days balancing until it is brought into balance. Only then does it return to regular operation. The algorithm might involve defining some threshold for balancing, such that we only balance cells that differ by more than the threshold amount from the lowest cell. This is important to avoid switching which cells to balance based on noise. Then we repeat some loop like this. For every cell, we check whether the cell voltage is higher than the lowest cell voltage plus the balancing threshold. If so, then we turn on balancing for that cell. Every once in a while, perhaps every minute, we repeat. You might call this an in-the-moment algorithm. An alternate approach might be to assess the state of imbalance and run balancing in a feed-forward manner. We estimate how much each cell needs to be balanced and then perform that much balancing while the pack is operating. We can't check that we balanced perfectly, but the system downtime is vastly reduced. The algorithm might look like this. For every cell, we evaluate whether it needs balancing. We estimate T-bal, the amount of time needed to balance the cell. What I have here as dVdt is a shorthand. Since the voltage curve is not linear, accurately estimating the time needed to balance is a little more complicated than this equation. And then we put the system back into operation and balance for the planned length of time. This algorithm has us make a plan and then execute the plan in a feed-forward manner. Another idea that I once heard but didn't quite see brought into practice is thinking of imbalance as a continuous process. The standard approach is for balancing to correct the presently observed imbalance and then stop. We wait to balance again until the pack has imbalanced itself again. A past colleague observed that imbalance is a continuous process. If you have a leaky cell to correct for yesterday, that same cell will probably still have the highest self-discharge today. If yesterday the pack had a warm end and a correspondingly unequal self-discharge, that will probably still be true today. So, perhaps our balancing algorithms should account for that. Perhaps we could look at how much we balanced last week or last month and apply that much balancing current during those times when we can't measure our imbalance accurately. I really like this idea, except for the storage requirement. This is much more complicated than the more standard approaches and requires the BMS to keep a log of which cells it balanced for how long. It can be fun and sometimes productive to consider creative, non-standard solutions. This is the end of the lecture on when to balance in the cell balancing video. If you liked what you saw, please help this course get seen. Share it with a colleague, share it with a customer, share it with a favorite college professor. And then continue the cell balancing lecture in the next video.